Hello, chemists, and I'm going to go ahead and apologize about the sound quality on this one. Left my microphone at home. So I'm going to be introducing you guys to the concept of an acid-base titration curve. And there's going to be a bunch of things that we need to know about this. So you'll be seeing these curves in your sleep. First thing to know is what kind of titration curve are we looking at? This is a curve that represents the pH of a solution as we add an acid or base to it. This one, you can tell you're starting with an acid because you have a low pH at the beginning, and you're adding a base to it because you have a high pH at the end. So if you were starting with a base and adding an acid, it would be the same graph, just flipped upside down, so your pH was high at the beginning and low at the end. There are a couple of kind of zones of this curve that we are going to need to know about. First one is the beginning. This is the point before we add any of the base that we're adding, so it's just the acid. We can calculate the pH of the solution at this point because it's just the concentration of the acid thrown into our usual Ka equation for calculating pH. So we know the volume, we know the concentration, we can calculate the pH. As we add a base to it, some buffer stuff starts happening. This zone here, kind of from the point where we begin to add base to the point where the curve kind of ticks upwards, is known as the buffer zone. That is when you've got a pH that is changing quite slowly. That buffer zone is going to be a little bit different depending on whether you've got a base that you're adding an acid to or an acid that you're adding a base to. In this case, we've got an acid we're adding a base to. You have both the weak acid and its conjugate base formed there. And you can use a Henderson equation to find the pH at any point in that buffer zone. So this buffer zone here is where you use the Henderson equation. That's a G, sorry. Henderson equation. So you know the concentration of the weak acid, you know the concentration of its conjugate base, and you can use the Henderson equation there. There is a midpoint. The midpoint is not the midpoint of the buffer zone. It is the midpoint in between the place where you started and the equivalence point here. We'll come back to the equivalence point. That midpoint, halfway to the equivalence point, is where the concentration of the original weak acid and the conjugate base are equal to each other. If we remember our Henderson equation, we know that if the concentration of the weak acid and its conjugate base are equal, then the pH and the pKa are equal. So the pH and pKa are equal to each other at that central point, at that midpoint. Okay, so that's three things so far. The initial pH is this one here. The buffer zone is this here, Henderson equation town. And this middle point here, midway between the beginning and the equivalence point, is where the pH is equal to the pKa. All right, third thing is this equivalence point that I mentioned before. That used to be called the end point. It's where, when we are doing a titration, we stop. It's where the pH begins to change very, very quickly. At the equivalence point, all of the weak acid has been reacted and converted to its conjugate base. The pH, in this case, is always going to be greater than 7 because we're adding a strong base to a weak acid. And the concentration of hydroxide is going to be greater than that of hydronium. Yeah, so that's the equivalence point. That's where, also called the end point, also called the EP. EP stands for both of those things, and it's where you stop your titration. After the equivalence point, your pH is going to change very, very fast until you get to this thing here, which is not called the end point, even though it is at the end. So that is when you've added so much of your strong base that basically you've got none of the weak acid left. The pH at that point, it's called the pH past equivalence point, is going to be equal to the pH of the base you were adding. Basically, you've wiped out all of the weak acid you started with, and you've got only base left. The pH up there is going to be equal to the new pH based on the concentration of hydroxide in the stuff you're working on, compared to the total volume of everything you have combined. So 5 things initial pH. I'll use a new color again. Initial pH here. Halfway to the buffer zone here, or sorry, halfway to the equivalence point here. Buffer zone here. Equivalence point here, and pH past equivalence point here. You should be able to calculate pH of the solution at all of these points. We will practice that in class today. Thank you very much.